Welcome to section 3.4, Complex Zeros and the Fundamental Theorem of Algebra. In this part 1, we will talk about imaginary and complex numbers, and we'll cover a few different things, but mainly talk about what an imaginary number is, the importance of an imaginary number squared, I squared, and then we'll also talk about complex numbers. We will define these mathematically and talk about how I squared is a real number. So getting into imaginary numbers, really what are they? Well, I'm going to introduce it with a little bit of an example. We all know that the square root of 25 is 5. Let's explore why that is. We can do the square root of 25 and we know that it's 5, but we know that because 5 times 5 equals 25. So therefore, this square root of 25 equals 5. We're looking for what squared or what times itself gives us 25. Well, then we need to ask the question now, can we also compute the square root of negative 25? That means, is there a number that when we multiply it by itself, it gives us negative 25? Well, we know that the rules of the real number system say that anytime we multiply a positive times a positive, we get a positive. So therefore, this can't be a positive number. Then, if it was a negative number, right, because these have to be the same, if it was a negative number, a negative times itself, a negative times a negative, is also a positive, so it can't be a negative number. That is why there's no solution to the square root of negative 25 in the real number system. In the imaginary number system, a different number system, we can compute the square root of negative 25, meaning something times itself can give us a negative. And that something is an imaginary number. The answer to this is not 5, but 5i. The square root of negative 25 is 5i. What is I? It is the imaginary number unit. Let's get a little bit more into what that means. By mathematical definition, an imaginary number is defined using an italicized lowercase I, and it is mathematically defined as the square root of negative 1. That is really weird. That is why it's not a real number. I is the unit that we have come up with mathematically to denote the number that when multiplied by itself gives us a negative. In this case, the unit imaginary number, I, when multiplied by itself will give us negative 1. Therefore, I is the square root of negative 1. Now, I just talked about multiplying I by itself. That would imply squaring I. Let's talk about what I squared is. To square a number means to multiply it by itself. So if I take I and then square it, that means that I'm taking what I is, the square root of negative 1, and squaring it. And when we square something that already is in a square root, the squaring and the square root essentially cancel out one another. I took negative 1 and I took the square root, but then I squared it again. Therefore, I squared is negative 1. That is a really cool thing because that means that I squared is no longer an imaginary number. It is a real number, which is a really neat phenomenon because when we get I squared, it really just equals negative 1. So this is a very important idea here, the fact that I squared equals negative 1. This is a very important thing that you should write down. So far, the two important things that we know are that the definition of I is that I equals the square root of negative 1, and that I squared is the real number negative 1. Here we want to simplify three square roots or square root expressions. So in number 1, we have the square root of negative 81, and we can break this down into the square root of 81 times the square root of negative 1, because 81 is the biggest perfect square factor of negative 81. And so the square root of 81, I like to cross it off when I write it, is just a plain old 9. I say plain to denote that we don't put the square root on it. That seemed to help students in the past. And by definition, the square root of negative 1 is I. So the square root of negative 81 is 9i. Okay, I added this at the top of the screen to remind us that I is the square root of -1. Take a look at number 2. We have two roots being multiplied together, and I'm just going to break each one down like we did already a few times. So the square root of -4 can be broken down into the square root of 4 times the square root of -1. Then the square root of -25 can be broken down into the square root of 25 times the square root of -1. Then the square root of 4 is 2. The square root of -1 is I. The square root of 25 is 5. I'm going to put a little multiplication sign there since these are all multiplied together. And the square root of this -1 is also I. So let's see what we have now. We're essentially multiplying four things together. I'm taking the 2 times the 5 first to get 10. And then I'm taking the I times the I to get I squared. We learned previously that I squared is a real number. It is -1. And if you notice, I've also added that at the top of our page here. So I squared is really -1. So what we have is 10 times -1, which is -10 as our final answer. For number 3, it looks very close to number 2, but it is essentially different because of the order of operations. We want to first simplify what's under the square root, the radicand. So what we're first going to do is multiply -4 times -25. When we multiply those two negatives together, we'll get positive 100. Therefore, we do not need any imaginary numbers for this answer, as the square root of a positive does not have any imaginary parts. Therefore, our answer is just 10. So far, we have found that I, or I to the first, is just I, which is the square root of -1. We found that when we square I, we get -1, a real number. But how about if we keep going? Well, what happens if we do I to the third? Well, how can we rewrite I to the third? We can rewrite I to the third as I squared times I to the first. Well, by definition, I squared is -1, and I to the first is I, and therefore I cubed is -I. How about I to the fourth? How can we rewrite I to the fourth? Well, a couple different ways. We can rewrite I to the fourth as I squared times another I squared, which can be rewritten as I squared squared. What is I squared? I squared is -1, and what happens when we square -1? It becomes +1. What if we were to do I to the fifth? I to the fifth can be rewritten as I to the fourth times I to the first. We've already found that I to the fourth is +1, and I to the first is just I, so we're back at I. It looks like we have a pattern here. We start with I, then we move to I squared, which was -1, then we move to I cubed, which is -I, then lastly we move to I to the fourth, which was +1. So it looks like our pattern goes I, -1, -I, +1, and then we've repeated. We started back from the beginning, which is I. What do you think I to the sixth will be? Let's see if we can figure it out. So I to the sixth, there's a couple different ways to get I to the sixth. You can do I to the fifth, right? But then you'd have to know the one before it. Like, what if we didn't know I to the fifth, right? Let's say we just did this as I squared and then we cubed it, since when we're raising power to a power, we multiply. So we can rewrite I to the sixth as I squared cubed. Well, we know that I squared by definition is -1. And what happens when we raise -1 to an odd power? It stays -1. That's cool. It looks like we are following a pattern here. What would you expect I to the seventh to be? If we're following the pattern, it looks like it would be -I. And you can work through that one as well. How would we work through it with an odd number? Let's see. I to the seventh, we want to use I squared. So I'm going to rewrite I to the seventh as I to the sixth times I to the first. But instead of knowing what I to the sixth was, let's say we didn't know what it was, we could rewrite I to the sixth as I squared cubed times I. And we know that I squared is -1. And then we cube it times I, meaning -1 cubed is -1 times I, which is -I. Now, that seems like a lot of crazy mathematical work, and I guess maybe it is. But let's say the only two things we knew were up top here, I to the first and I squared. Could we figure out some crazy exponent knowing only those two things? What if we wanted to know what I to the 73rd was without going through all 72 prior? We only need to know that I to the first is just I, or the square root of -1, and then I squared is -1. Let's try to break down 72 into that. Okay, so we want to break down, I meant to say 73, sorry. I had 72 on the brain because that's our even number right below it. So we can rewrite I to the 73rd as I to the 72nd times I to the first. I to the 72nd can be rewritten as I squared, and then 2 times what is 72? 2 times 36. And then times that I to the first out there, which is just I. Well, we know that I squared is -1. So I'll replace that. Then I'll move over here. -1 raised to an even power would be +1 times that I. Therefore, our final answer is just I. And so if we kept going in that pattern, 73, if we did that all 73 times like we were doing before, we would be left with I. So it's kind of a neat little extra thing and working with powers of I. The last thing that we're going to cover in this video is a complex number. And I really like this visual that I found online. I just Googled it. We've talked about the real number system, and this is the number system we've talked about before. The real numbers can be divided into the irrationals versus the rationals. And irrationals we know is like pi and √2, weird decimals that don't repeat but go on forever, all that kind of stuff. Rational numbers are those that can be written as fractions, like our counting numbers, whole numbers, all integers, and weird fractions even. Then if we zoom out, if you imagine zooming out on this, we have that the real numbers were really just a part of something even bigger. It's kind of neat. It reminds me of like the universe and zooming out. And complex numbers encompass all the real numbers and the imaginary numbers. Complex numbers are a combination of a real part and an imaginary part. So like the number 6 plus 7i or 6 minus 7i. It has a real part 6 and an imaginary part 7i. Or this guy right here. -23 plus or minus, it doesn't matter, 2/3 root I. All right, so -23 is the real part and 2/3 root I is the imaginary part. So that's pretty cool. By definition, a complex number is a number of the form a plus bi. And this plus could be a plus or a minus, meaning the b could be a positive or a negative number. A is the real part. It's the real part of our complex number. And the bi, that's the imaginary part. If you're ever doing any computations with complex numbers, a number that contains both a real and an imaginary part, you want to make sure that you write the real part first and the imaginary part second. So just like these are written here. The last thing I want to talk about, I think I already said the last thing, sorry, I forgot I added this at the end, was how does this all fit into our learning? Well, we have been talking about finding the zeros of polynomials, and if that 0 was real, it's where it hit the x-axis. If the 0 was imaginary or complex, we could say it either way, we couldn't see it. And what we're going to be doing is finding all of those zeros, not just the real ones anymore. So I'll do a real quick example, and I'll just use a parabola, a quadratic function. And let's say we have a parabola that hits the x-axis 2 times. Well, according to the fundamental theorem of algebra, since this is a quadratic function, right, degree 2, it's going to have a total of 2 roots, and in this case, they're both real because we can visually see them. They might be weird numbers, but they're real. Now, if we had a parabola that only hit the x-axis and came back down, it has one real root, but that real root has a multiplicity of 2, meaning it occurs twice. Again, it has a total of 2 roots, and this one had 1, but it occurred twice, so technically 2 as well. So far, these are 2 examples of quadratic functions, degree 2, and both of their roots, all of their 2 roots, have been real. But we know that roots can be real or imaginary. So if we had a parabola, like this navy blue one, that lied above the x-axis, or if it looked like one of like this, if it lied completely beneath it, it never touches the x-axis, meaning both of those roots would be imaginary, and they would look like maybe plus or minus 3i, or they might look like 2 plus or minus the square root of 5i, something like that. These are just examples that I'm giving. And we can find those by using the quadratic formula. So when we are finding the zeros for polynomials, and I used a simple example here of degree 2, but let's say we were trying to find all the zeros of a higher order polynomial like degree 3 or 4, some of those roots might be imaginary. Imaginary roots do come in pairs. That's what that plus or minus is as part of the quadratic formula. So we need to understand how to work with these complex numbers that contain I in order to be able to find them as zeros of a polynomial. So that's how this fits into what we are currently learning.